All right, question number two is dealing with the speed of light and how it changes. So not only like what its new speeds are, but kind of how it changes, what changes, frequency, all those things. So we'll go through those different things. First off, we have our table of values here. N is the index of refraction. N, and its equation, N equals C over V. That's the equation for N and its relationship to the speeds of light. But you're trying to find the new speed of light in Emerald. And so this equation, the N and the V just kind of swap there. And so we have V equals N, whoops, V equals C over N. And so now we can just kind of plug in 3 times 10 to the 8th. Remember, C is 3 times 10 to the 8th divided by N, and we want for Emerald, so we'll come over here to 1.57, and I get a velocity. When I solve that, I get a velocity of 1.91 times 10 to the 8th. It's always times 10 to the 8th meters per second. It's not going to slow down that much. All right, now next time we've got one that's found to travel at 2.29 times 10 to the 8th meters per second in some new material. What is its index of refraction? Again, you've got the equation, N equals C over V, and so that's going to be 3 times 10 to the 8th divided by our new slower speed, 2.29 times 10 to the 8th. Notice that that also is a times 10 to the 8th. It's always going to be a times 10 to the 8th for the speed of light in anything. Nothing's going to slow it down more than times 10 to the 8th. We don't have any indexes more than 3. Anyway, that comes out to be 1.31. And if I look up to the chart here, 1.31, it looks like water maybe the alcohol there. Or maybe ice. Oh, it looks like it's ice. 1.30, but that 9 is going to round it there. So it is ice, which is about 1.309. That's pretty close to ice. Which material does light travel the slowest? So slowest would be the largest index. So that's going to be diamond. Diamond is 2.417, and that's the largest index of refraction. Right? Index of refraction. The bigger the N, the slower the light. All right. So now, kind of our different trends here. As light travels from water into air, the angle relative to the normal. So this is referring to, you know what, let's kind of do this like straight along across. I'm going to have the normal here. I'm going to have the light coming up this way. And so that's its index incidence, right? And then if it went straight, it would do that. But since it's going from water into air, it's actually going to go over here. It's going to bend away from the normal and create a larger angle of refraction there. And that's because it's going from 1.33 into 1.0. So as light travels from water into air at an angle relative to the normal, yeah, there it is. The index of refraction increases or decreases. Well, it's going from 1.33 to 1. So 1.33 to 1, that's going to be a decrease. Speed of light is actually going to increase. The wavelength is going to spread itself out. When the speed increases, the wavelength spreads back out because frequency doesn't change. The frequency of light stays the same. We said that. Frequency stays the same. Angle of refraction. I think technically what we're saying here is it gets bigger, it increases, but really this would be like relative to the incidence. Right? So it's asking you like these two angles here, comparing this one to this one, how do they compare? And in this case, the refracted angle is bigger than the incident angle. And so that's why we say that that is going to increase there. But really, there's only one angle of refraction there. So does it get bigger, smaller? That's kind of a weird question. But relative to the incoming angle, the refracted angle is bigger. And that's what it's asking there. And then again, we say the light bends away from, let me go back to a different color. Light bends away from the normal because it's getting bigger to that. All right. And then these last two questions are dealing with light actually moving through the air. It does change. I mean, it takes time to travel. And so you want to be able to calculate how far the light moves when it's traveling. So red laser beam, we have a time there. The time equals 2.51 seconds to go to the moon and then back. Calculate the distance from Earth to the moon. Now this is a little bit tricky. Again, red laser burst takes 2.51 seconds to the moon and back. So the time to go just from Earth to the moon, just to go the one way, would be 2.51 divided by 2. And so that's going to give us a time of, what is that? 1.255. 1.255. Yeah. And so now we can use the velocity equals distance over time. We're trying to find the distance there. So this becomes distance equals velocity times time. And so that's going to be 3 times 10 to the 8th meters per second times the 1.255 seconds. And so that's going to give you a distance of 375,500,000 meters. And we can leave it as that. Again, you can split it in half. Another way to do it would be to find the total distance using the 2.51 seconds and then just dividing that distance by 2, because that would kind of be, if you use that, that would be there and back, right? So the 2.51 is there and back, but we only need half that. So if you calculate it with 2.51, you need to divide that in half, and you'll get the same number there. All right, will the time for a green laser burst travel to the moon be greater, less than, or equal to the time it takes the red laser? Well, assuming we ignore the atmosphere and it's not really, it's pretty much negligible, it really is the same. Same time, because they move at the same speed. Light, the color of light doesn't change its speed in a vacuum. Now, if it were in glass or something like that, then the color would matter, but it's not, so that's it. All right, so that is question number 2.